All right. And what I also want you to remember is one thing. So please register for the exercise session. So every Tuesday you register on the Google Sheet, put your name if you want to go on Zoom or if you want to go in the real room, put your name on Tuesday so that then on Thursday we have space for you. And then you see in the same sheet, you will see the rooms, which we will tell you on Wednesday. So don't forget this every Tuesday. All right. And also, if you want to have a look already at the first small project that comes up, that will be aligned with the first 6 labs. So have a look at that, try to find teammates slowly. There is time, no rush, but already have a look at the project descriptions. Don't forget that there's a small project in the course. Project 1 is a warm-up, 10% of the grade. And then we have project 2, which you start in the middle of semester. You see all this on the webpage, where you also can do this in groups of 3. Okay, so and yes, I will share the second lab today. That's the question we got on Zoom. Sorry, so yeah, second lab will be up every Tuesday. So, or maybe we can do it on Monday even. So don't worry about the second one yet, but make sure you're fine with the first lab this week. So, okay, so we finished linear regression last time in the Rolex, and regression models in general, and even linear ones in particular, they are the fundamental building blocks of machine learning techniques, also of neural networks. Another fundamental building blocks that we do need is cost functions, which means this is just about what are we actually optimizing. They're also called loss functions, but maybe cost gives a better intuition what it is. So, and yeah, don't hesitate to ask questions anytime. Raise your hand here or on Zoom. Happy to take it. And so that's for today. Why do we need a cost function? So this is about what is a good model, what is a bad model for a given data set. So let's consider a data set. And here, let me make maybe 2 variables. I observe one feature, x and 1, and then I observe a label. So that's my data set. It's here. So here are my data points. And the question is now, what is a good model for this data set? So one model I could fit is for example, this 1 parameter model. Here is a 1 parameter model. What is that? What is a 1 parameter model? This is just something which is defined by 1 number. And the model, what is it going to, no matter what data as an input you give to the model, it has to give an answer, what is the prediction for the 1 data point. So here's my 1 data point. That's my x and 1. So, and then you have to ask the model, so what is the prediction for it? And that's here. So the funny thing is that this model will not even look at your data. It will just always answer the same. So it's a very naive model, but that's a valid model, and that's what we have here. So this is the first model we have. All the models, we usually call them F described by W, by the weights, and it depends on the input. And that's the prediction it makes for data point xn. This one, it ignores xn, it will just answer W0 every time. So here is a second model, which is 2 parameter model. Again, depending on the data point xn. So xn is a data point. So it might have several features, right? It has usually d features, but in our case, the data point only has 1 feature. So here the features are the x-axis, right? So we are here on a 1-dimensional example. So in the real numbers, and of course also the label is just a number. That's always the case. So don't need to write it. Okay, that is a naive model. Let's have a different model. So here's a different model. That's the model number two parameters. So that you would say that this is a bit a more advanced model. So more complicated, and this one is maybe more simple. All right. Now, why do we need cost functions? We need that to distinguish between simple and complex models, because there's so many models to choose from, and many of them are just bad. I mean, this model here is a terrible model for my black data points. So I don't want this model. But how do I quantify that this is not the model I want? How do I say that these two models here are reasonable and which of the two is better? So which are the right W's for fitting my data? So the W, again, you see it here. So the three weights here, well, there's just, the second model has two W's and the first model only has one. All right, and this is what we're gonna find. And the cost function is gonna tell us which one we should prefer. And so I'll also enter this here. So what the cost function will depend on is, it will depend on, so if my data point is here, it will try to measure how far away is my model from the data. And by data, I mean the value y it should be, right? The label I want the model to predict, the true label is called yn, right? So, and the model is not perfectly giving that yn, right? Somewhere else. So and this distance here from the red model to the black data point, that is the error, and that's what my cost function is going to capture. So capture the error and then measure that and punish it more. Higher errors are going to be more punished than lower errors. Does that make sense? So so we remember, I'll define that the error en, I define it to be always the ground truth, as we call it. So the thing that we want it to be, we observed yn, and then the prediction that we actually made on our data x. So my model predicts something on my data point xn, and what it predicts, that's the f, right? And what it should be, that's the y, and the difference is the error. And now we are ready to define the whole concept of a cost function. It's very simple. It's just, so the cost function, what is it talking about? It's saying that the cost of what? So it's the cost of the model, of the weights, telling us what is a good model, what is a bad model. And the way it's defined is, it's just going to be the average cost. We have n data points, so capital N, small n going from 1 to capital N, of the cost applied to this error function of the ith data point. Does this make sense? So whenever you predict some number, it could be too high or too low. And then if you want to punish this differently, how much you are too high or too low, that's what the cost function does. And later we're going to use this to find a good model. That's what we're going to use to do the training. We will ask the machine learning training algorithm is going to find the weights which are minimizing this cost, which means it's going to fit the data as good as possible, which means that over the whole data set, I want that this cost function is as low as possible. So that's why you think maybe this model here will have some cost, but the model here, which is a much worse, that one will have a higher cost. And the two models we have here, they will have a better cost than a very bad model. So that's the idea. Okay, so why? So you could define anything to be a cost function, right? And so you have full freedom there, and that's actually also, this part of this is quite challenging to do. So if in a real machine learning application, that's really something you do spend time on, right? Because this cost function should reflect what your customer really cares about, right? So sometimes it's much worse if you predict too high than you predict too low. So it's really kind of your job as a data scientist to find a cost function which reflects what your customer wants, or what the application what really measures the quality of the model in your use case. So what we usually do a bit more practically is that we usually just use symmetric cost functions for convenience. It's not a must. What does that mean? It just means that, yeah, here, if you are some number below, you pay the same as if you're the same number too high, right? So that is one reasonable thing for cost functions to have in some scenarios. Sometimes it's not, right? If you are a self-driving car and you are at a stop sign, the cost of predicting that you can drive as a mistake is a bit higher than the cost that you predict to not drive, right? So that would be a case where you would need an asymmetric cost function. Or if you deal with medical data, of course, also if you give a diagnosis to a patient, there might be, you have to be more careful if you want to give yeah, this type of diagnosis. So maybe false positive sometimes have another effect than false negatives. So so I talked a bit about classification, right? But for now, you should think of this as a regression. So for regression, this is now a bit easier to understand, but the concept is going to be perfectly fine for both classification and regression. But for the first few lectures, we stick with regression. Another reasonable property is to have, what do you do with the mistake? So what you also want to do is that the cost function should be a bit robust, and we're going to discuss this in a second. So if there's just one point which is extremely wrong, then you don't want that point completely dominates your entire cost function, right? There are n points here, but if one of them would have so much influence to overshadow everyone else, then that's probably not a good cost function. So you would really like to make sure all the points are contributing to it, and all of them get a bit of attention, and all of them get reflected in the cost in a reasonable amount. So if you do a large mistake, it's probably the same as if you do a very large mistake. So that should not be a big difference, and that's why often some cost functions have if you look at it dependent on the error, many of them look a bit like this, right? When you have zero error, then the cost is zero, and then so if you have like whatever at some threshold you will pay a cost here, and then if it's higher, then you want it to go a bit more flat, because it doesn't matter anymore if I have an error of 1 million or if I have an error of 10. But it really does matter if I have an error of 0 or an error of 1. So that is a big difference. So that's one possible shape of cost functions, and the error here, I draw it for positive for simplicity. We will get back to this. So what you're going to do is we will discuss a bunch of cost functions which are very widely used. You probably know them already, but now you will maybe see on a slightly different perspective to say what are they good for and why are they good for machine learning for some regression application. And then we can discuss a bit like what are the pros and cons. Like some of them have a statistical property that it means that they give a very accurate model, and the other ones might have different properties. For example, they might be more efficient to compute. So there will be a bit of a trade-off there. We'll not go into full detail, but we will mention it a little bit. So, okay, so the first one, I'm sure you have heard of it, right? So this is the mean squared error. And if you look at this in the middle, so let's look at the formula. So this is exactly what I wrote in the previous slide, right? I said we have the error. So how far away is my model? Model predicts this, right? And the ground truth y is this. So how far are they away? That's what we have here. And then the actual cost function here comes afterwards. So that's happening here. It's taking this error, and it's taking the square. So which is exactly what we discussed before, because we said, okay, it's reasonable to look at symmetric cost functions, and of course that they should be growing as well. So the more error you have, the more cost you want to have. So this is the cost of my data point number n, and then I just do this, sum this up over all data points. So does this make sense? So the cost of data point n is this error squared. It doesn't matter what the model is, right? The model is just something, whatever it predicts. So the f is kind of a black box. Whatever it predicts, you measure the squared error. And I think all of you have heard of this. And now, but let's see. So why is this? Why does this make sense to tell us if this machine learning model was good and bad? So can we really use this cost function to compare different models and measure their quality? So we will again use this very naive model. Actually, we use this flat model, the one parameter model, which I showed you on the previous slide. So this is the simplest model you could imagine. It gets a data point, it ignores the data point, and it will just output W0. Whatever data point you throw at it, it will always give the same answer. It's like this random number generator in Dilbert, which whatever you ask it, it will always answer 13 as a random number. So that's the model, and now I want to look at what is the cost function of my model. This is just a really simple example to ask it. So here on the table we have W0 on the horizontal axis, which model we have. So we could have a small or a big W0, and now we want to see how does that affect my cost. And of course it depends what my data is, right? So I also have some data. So maybe let's do this here. So let's imagine we have maybe 4 or 5 data points, and okay, let's do it step by step. So let me just start with one data point, right? So here is my X. So actually all the X's are here. Here's my first data point. So the data point has label 1, and the model predicts 1. So that means the error is 0. So what I'm going to fill in this table is the mean squared error, which is the error of the ith point squared. So that's what I'm going to fill in, and remember the error, of course, is this. So it's 0 if my model is 1 and the data is also 1. If my model is 2, that would be the example here, that if my W0 is higher, then you can see I'm too high for my point. I over predict the data point, so I actually have to pay, and then all I'm going to say is that the error is 1, and if I square it, it's 1 squared. And what I'm writing here in the table here is I'm writing the mean squared error of my first data point. The point is here, right? Depending if the model is here or wherever the model is, right? So this is the error. I'm just plotting this for every model on the horizontal axis. Good, and then, but we don't only have one data point, we have another data point. So here is the data point 2, y2. And now which model is the best one for that point? It's a different one, but we will only find one model. So, but what we can do is just for any model you could take, for any candidate, see how much error it has. So if your model is 1, data is 2, then error is 1. Here, if the model is 2, then you're perfect, you have 0 error. So that's the the cost of my data point 2. So this thing is the cost. So that's what I'm plotting here, right? So. And so on. And then you can finish this exercise. So I have more data points. And I will just see what's happening here. Yeah, I let you complete this table. It takes me too long. What I want to do is now I want to have the whole sum over all my 4 data points. So what's the cost of all the 4 points together? And that is very simple. So I will just add up all these things. So this is 1 plus 4 plus 9, which is apparently 14. And then here, if my model happens to be 2, that's the one I have on the right, then I actually get a lower overall cost, which is quite nice. So then the total cost is only 6. Same as here, if you do the math. And then when the models go higher vertically again, so the red line moves up here, then your cost of that model on this data set of 4 points gets higher again. And so on. So you get the idea. Okay, why am I computing this? Because I want to ask which model has the lowest cost. So here are all my model candidates. So which one of these is the best, which fits my data best? And now that's very nice. I can clearly see that model 2, which is actually the one I had drawn here, that model has the best cost. For what? For these 4 data points I have here. So here is why 4. Okay, nothing special. So of course you wouldn't do this by hand. Usually you would do this in Python. But why we're doing this exercise is to study how this best model here, how is that influenced by the data set, and if there's an outlier in the data set or not. So, and that's what's gonna come next now. So now, what if I give you one more point, and that point happens to be 20, so it's very high up, so you just got one more data point. So now that point here has a pretty high cost to your model, right? It's this guy is pretty far away, so that's we're gonna see that in our error. Let's be more precise. It's actually so the model is 1 and the truth is 20. So the difference is 19. If you square it, is a huge number. So that data point, the new guy, has a very, very big loss or big cost function. And then the higher you shift your red line, your model. So if you make your model be maybe 7, that's the highest we have here. Then you have 13 squared, that's the error cost, which is still pretty high. So if you now sum up everything again, you will get much different values. I don't remember them here, but there's some help on the bottom. You can do this when you're bored by me talking. All I'm going to tell you is that the best model in that case is a very different one. So in that case, I'm claiming that the lowest cost is when your model is this one here, 6, so very high number, which makes sense, right? Just saying that if you have this outlier point, and then this one will shift the whole model very far. So one data point was able to shift everyone's model to a very different place in the space of models. So that's interesting, right? So it's not clear if you want that. So that means it's not very stable to having outliers in your data, and that's really the key takeaway from this slide here. So here was the best model for 4 data points. best model for 5 data points looks very different. So it's not stable to outliers. Any questions on this? Too fast, too slow? Then outliers. So what do we mean by it? So I think there's no very precise formal definition of an outlier, but what it means is really that it's one point which has come, a data point which has come maybe through a mistake or has come from a different cause than what you expect it to be, right? So if you look here, so this is some people have measured one number, which is here speed of light, whatever, and then you get a whole distribution of measurements, right, which are thousands of values, and they're all kind of similar. They have this whatever Gaussian shape, all nice. But at some point, maybe you get a point here, which is slightly below 0, or here a point -40, which doesn't really make sense for speed of light, but that happened to be in your data set. So those are the points we would call an outlier. But we cannot give a mathematical proof that this point has come from a different distribution. We don't know, right? Nature gives us this data, and we're just assuming that nature gives it to us in some probability distribution. For example, also a Gaussian, this probability distribution has a long tail, right? So it will sometimes give you points very far away. I'm not saying that the speed of light here is Gaussian, of course. We don't know what it is. I'm just saying that, yeah, sometimes you get data which you're not sure it comes from the true distribution, or if something strange is going on, and then these are outliers. And practically, if you have them in your data set, which you always do in large data sets, then you might have a problem to use those, because they will distort your model into a crazy place. So you don't want them to have so much influence onto your training, right? You want that every point has about a similar influence. So that's why mean squared error is not a very good loss function always. It's still extremely widely used. So even neural networks, very often you use mean squared error as a cost function. It's perfectly reasonable, and we will also talk more about it. It's mean squared error can be a good cost function, but it's not, but not always, right? In this case, I showed you an example where it's not going to be appropriate to define the best model. So, okay, so mean squared error, maybe not always ideal if you have outliers. So what else can we do? So it's very simple. You've probably also seen this one as well. So if I take the same quantity, my same error between prediction and model, instead of squaring it, I can say, let me take the absolute value, right? That's something a bit, the next smartest thing we can do, and it is actually quite a smart thing. And well, you would think it's very simple. It is, but it has a big effect. So, and we can see that easily in the very same example again. Again, we will have our one parameter model. Again, it's just being W0. And again, we have our data points as before. We have 4 points like this, and then we have one outlier there. And if you fill in what the errors are for all kinds of different models, let me quickly do this. So it's the same numbers as we had before, except the numbers are not squared now. That's the only difference. And yeah, and so on. I'll spare you in a second. Anyway, if I compute this for the first 4 data, then I have a total cost function of 6 respectively, or 4 if you take the second model. So I'm using the whole sum here. I'm not dividing by n. So I'm summing all the cost in the table. That's why here it's n times the mean absolute error. So mean just means that yes, you divide by number of points. It doesn't matter for machine learning purposes. it doesn't matter because when we will do optimization with this cost function, it will not matter if you divide by n or not, because the gradients, they will do the same thing. They will not change anything interesting if you do this. And also we don't even care so much about the value of the cost in machine learning. We just care to find the model W which gives us the lowest, right? But if this cost function is scaled by 10 or by n, it doesn't matter. So let's see the overall cost over our models, depending again where we put the model here. That's again on the horizontal here. And okay, where's the best model? It's here again, model 2 and model 3. So it sounds the same as we had for mean squared. So there's nothing. Why are we even talking about it? It's giving you the same answer, right? What we are interested here is the arc mean, right? The W which makes his cost smallest. So that's W2 or W3, same as before. But what is interesting now is that if we again add this outlier point, then if you sum this up, then you get 25 for the first model, and so on. Sorry for my writing. So what I'm saying here is that with the outlier, the best model is model 3. So almost the same as without the outlier. So 2 or 3, and now the best model for 5 points is model 3. So it's the same. So same as before. So it's not affected by the outlier point. So that's very nice. So we see that if we decide which model to take by the mean absolute error, then we'll be much more robust. We don't have any problems to this particular outlier. Okay, so we have seen 2 cost functions, and next question will be, so yeah, which kind of interesting models as well can we use? So that's going to be then, that's like in neural networks, like what architectures do we design? So that all goes into the FW, right? So how to express the function, which is your model. So that's a whole other question. Once you have such a FW, then you can use a cost function to decide which is the best W. So that's why we need cost functions. And so now what we discussed so far was saying that, okay, the first cost function was bad in terms of statistical property, it was not robust to outliers. The second cost function had a bit better statistical property, but that's not the entire story of cost functions. So what you also have to be aware is, so how efficient is it actually to look at this thing and find the best W? That's the training. So that's what we're going to discuss next week on optimization. But today I want to just briefly tell you that yeah, some cost functions have a different shape than others, which makes it can make it easier or harder to optimize. And we will not go into detail. So there's other courses which go more into detail for optimization. But what I want to mention is again something you already know, which is a convexity of a function. So what I'm talking about here is the cost function depending on En whatever. So if that's your cost function, the mean square function looks a bit like this. This one is a convex function, and you know why that is, right? Because every point in between 2 points is having the interpolation is higher than the function at the interpolation, u and v. So yeah, if you look at 2 points, then you can see that the element here is above the function. So this red function is convex, which is can be a nice property. Why are we mentioning this here? Because this can be a computational advantage. It can make it easier to find its optimum. So that's something that we will mention again a little bit next week when we talk about optimization. So the computational, even if statistical properties are not perfect, maybe this one will make it easier for us to quickly find the best W. So that is a nice property, and this is just a recap. Basically, if you have the same thing with a strict inequality, then that is called strictly convex as a property for functions. And you probably also have seen the same property for sets, which we'll also mention briefly next time. And I want to give you an example of a function which is not convex. So that's one which would be not convex. Yeah, I think you have seen this. Why is it making it more convenient? So the mean square function is convex, and it does make it easier to find the minimum in the sense. So maybe there is if it's a strictly convex function, then the one nice thing about it is that there will be one strict minimizer. I mean, one unique minimizer to the function. So you know that if it's going up on both sides where you are, then you know that you must be at the global optimum. So that's why it's nice to have a strictly convex function. So just I want to give you one caveat. So when we say what does it mean mean squared error is convex, so this can mean two things. So it can mean that are we talking about mean squared error as a function of the error E, or are we talking as a function of the weights? And that's something which is often forgotten, and I want to remind you not to forget. So when we say that mean squared error is convex, so it makes it easier to find W, then we want to talk about the whole function as a function of the weights W. Because we want to find the W minimizing it, right? So, okay. Any questions on this? Or hope I didn't confuse you too much. So, small exercise for you is to actually prove this for the exact same example that we have seen just before. So, this is just a tiny homework. And again, this is exactly, you want to show that this is the mean square is convex as a function of the W as of the model. So that's what so again, W is the thing we're interested in, and right, so it depends on W. Okay. That's nice. And then before we do the break, let me just show you. Actually, let's do this after the break. Maybe it's good to take a break now, and let's restart. Yeah, regular time, 1/4. It's okay. Let's see if this works. Oh, it's a bit too dark. Okay, so. Okay, we were discussing different cost functions. I want to comment a little bit more about the robustness of cost functions and also their computational properties. And let's see, for the mean squared error, we saw that it did have this property that it was not tolerant to the outliers, but then we saw that it was we're going to see later also that it's going to be very efficiently to optimize. So also in the chat, there was a question like, so is there a cost function where you have the best of both worlds? So is there a cost function where you have both good statistical properties, but at the same time, it's very fast to optimize. So, and that to tell you the answer, I don't know. So it's hard to get both. That's why it is often a bit of a trade-off, and that's also what I'm trying to illustrate a bit more on this picture here. So when we look at some different options we had, right? So now we already tried one or two of these cost functions, and I want to discuss a few more. So if you look at this as depending on the error En, so in the middle is 0, and now we can plot a few different cost functions. And if you want to look at, for example, the blue one here, so then you can see that it has quite an interesting property that first it's 0, of course, basically. So all of them are 0 if you are at 0. And then they grow, all of them. So you grow, and then some of them keep growing and some then flatten out, like this blue one here. By the way, can you see the slide well, or would you prefer if I turn off the light? Who would? More dark is better? Or like this is good? This is good? Any? Raise your hand. This is not good. Okay. Yes. And keep asking the questions on Zoom. So that's great. We can answer them. So now we have different, here we study the cost functions as depending on the error. So I also want to use this opportunity to quickly come back to be very precise here. That we said MSE is convex. So that statement is meant as a function of the error. Then it's always convex. But depending on what your model you have, you might have a very different combination of the two if you ask about with respect to the weights. So if you want to have this statement to be fully technically correct, then you would need to say that, yeah, mean squared error is convex if so, or if you really use for a linear model. If the linear model is like this, right? It's taking the data, multiplying with the weights. That is what a linear model does. W times X. So if you have linear models and then on top of it you use the mean square cost function, then the whole thing is convex in the weights. And if you just want to have any model you like, then you can say, okay, yes, mean square cost function will still be convex in the error, but not in the weights, because your weights go through a crazy neural network and then you get a prediction. So here, just be careful of for what model do we talk about. The model is of course important if you talk about the dependence on the weights. So that's this, just to clarify. Function. And if you have linear, it's also as a function of the weights. Okay, so let's compare a few different cost functions. So and here we can actually see a bit more what we meant by robustness. So again, here's everything depending on the error. It doesn't matter at all here what the model is, right? So because we just plot the error. So here is an interesting thing that you see that this blue function stays flat after it has reached a certain value, like 5 or so. It will not increase anymore. It has flattened out. So what that means is that exactly what we had as our initial motivation there. We were saying you would like very large errors, like if you're here with like 10,000, you would like that this value, the price you have to pay here is still manageable. So that's why this you would like this to flatten out, because this will give you the statistical robustness. So this is you can say this is robust, right? Because if you have an outlier in this scenario, that's a point which is very far right, then you pay exactly the same. So you can see that it's not sensitive to outliers. They are treated the same way as regular data points. So that's what it means to be robust, that it flattens out, which is nice. However, there's this like another property which we see here is that the blue function is actually not convex. So as a function of E. Why not? Well, because I just draw a small counterexample for you. I was drawing this line connecting two points on the function, and we see that the connection is below the function, not above. So this is a counterexample. This proves that the blue function is not convex. So that's okay, right? It's just something to keep in mind. So, and also, well, what that's we were going to see later next week, that this is going to make it a bit harder for us to then use such loss functions to find the best weights, which we use by, usually we do optimization to find better and better W's, trying to minimize this cost function. We will usually use gradient descent diagrams. So that's what we're going to do next week. And so we'll briefly start touching on this today about how to find good models, no matter what the cost function is. Okay, and then let's not forget the two most prominent ones, which we already know. So the black function, this is really the mean squared error. So this is just the en squared. And then we have, what else do we have? The green function. So this is the mean absolute error. That's green. And you know it's defined as absolute value. So that's this, I mean, for 1 point. And if you have more points, of course, you get just summed up or all points. Then the red and one is also very well known in statistics, the Huber loss function, but we're not going to use it. And then this other more advanced loss functions, mainly coming from the field of robust statistics, which is trying to address exactly this challenge we said here, that we would like a function, a cost function, a loss function. We would like it to have both these properties to be robust statistically. And at the same time, hopefully we can still find the minimizer. So, I mean, the minimizer in En is easy to find, but we want to find the minimizer in the weights, right? And there's a more complicated model which is used and makes a prediction, and then we measure the En, and then we have the cost we pay. So that's this for different cost functions. And I have a little bit of, for those of you who are interested to read more about it, you can look this up a bit more on Wikipedia and so on if you want. And also you can see that, yeah, minimizing functions is actually quite a difficult topic. That's actually our next topic. So that's just 2 pointers we have here. Okay, and so before I will just use about 15 minutes from optimization before we stop. But before I do that, I just wanted to come back just a little bit on the linear regression part, because there was one thing which I wanted to comment a bit more is about this. If you do linear regression, do you have more features or do you have more data points? So that's something I just want to spend 2 minutes on. So remember, of course, linear regression is very easy, right? So we have data, every data point has capital D many features. And now what are we doing here? We're trying to fit the blue weights such that they fit the data. So that's what we do in linear regression, no matter what loss function you use. But so we're trying to find all these W's such that the X's are fit, which means that this thing is close to the true Y. Now, what I want to discuss is the D versus N, right? So that's the question. So sometimes you have more data points, and sometimes you have more features, and it's not clear what is making it easier or not. So actually, we will also come back to this next week when we discuss that least squares. In some cases, you can find in closed form what the best W is, and then again, it matters a bit like how many features do you have. So this D versus N is kind of interesting. So the interesting thing is if this also determines a bit if you have one true solution, one best model, or many models which serve as the best model. So this you can see here W. So it just in this very simple example is we have one data point and we have two parameters in our model W. So what is happening here? So this is the data point is here, right? In X and Y, that's my data point. It's just a one number, and then I observe a Y value. But now there's several models which can fit this, right? We actually saw this, right? We can fit the straight model, we can fit this model, we could also fit that model. All of these models, they perfectly fit the data point. So that's an example where we have n equal 1 and d can be higher, right? So here we have two parameters. The two parameters W0 and W1, they can be chosen. And what that means is if you have more parameters than you have data, then often it means that your problem is underdetermined, that there's many optimal solutions. Everything which gets zero cost here, which fits the data point perfectly, everything is a perfect model. So if we just look at the cost function, we can actually not say which of these red models is better. They're all good, right? We don't know which is the best. So but is that a problem, right? It's actually, I would say it's not a problem, right? Because we care about the cost. We don't care so much that there are infinitely many models which perfectly fit it. And that's also what we often see in neural networks, that neural networks are so expressive, so powerful that they can fit any data perfectly with zero training error. But that's not solving the problem, right? That's not a good thing. But they can fit any data perfectly, but there are many ways which can do that, right? If you find one solution, then there might be another solution which also perfectly fits it. There's many of these solutions who are like the red lines here. So if you really understand linear regression perfectly, then you really also understand most of the phenomena in the neural networks, where also there you have this phenomenon, you have more parameters than you have data. And then of course you can also have the opposite, right? So what we just mentioned now is when the model is over parameterized. There's more parameters in the model than needed to fit. So we can fit very easily. So the opposite, of course, is also very common, that this is like the big data regime. That's kind of the opposite problem when you have many data points. Again, it's not a problem, it's just a scenario. So if in the opposite regime you have much more data points, then you have features D. So that is also very realistic, no matter if you use neural networks or not. That happens very often if you just have a gigantic data set. And also in statistics, you always have sometimes this is called statistical regime. So because there you care that if hypothetically, if you had infinite data, would you get something like the truth or the perfect model for actually the test accuracy? So that's why statistics traditionally has mostly dealt with this case here. If you get many data points, then can you get more and more accurate to see what your model is, right? So here in machine learning, we don't care so much if there is one correct model or many, but what we do care is about the cost, right? And here, so if you, maybe that's also a good thought experiment for you. So or maybe you tell me, what would be a scenario with one-dimensional feature, and how would my data points, what's a simple case with some data points where I have this, where I cannot get perfect fit. So can you give me two data points which I cannot fit with linear? Yes. Exactly. Yeah, you're saying I can have the same X for two different Ys. That's exactly what can happen. This is perfectly possible, right? That, yeah, it's just that customer has given you two images of the same cat picture, and for one of them, customer tells you it's a cat, and the other one tells you it's a dog, right? There's nothing you can do, right? the customer is king, or they have labeled the data. The data says that the y is 2 here and the y is 1 here. Happens to be for the same x. So you can, this is very realistic to have this in your data. And now you can fit the model, you can fit this, or no matter what you do, is you're not going to fit the 2 points, right? It's impossible. So that's why, so now we are in the under parameterized setting. So what's happening here is that the overall cost will not be 0. It will be higher than 0, right? Because no matter which model you take, you could take the craziest neural network you have here. It will always give the same answer for the same image, right? So it's not going to solve this problem. So any model you choose, it will have a big cost on this data set. So I mean non-zero cost. So that's what it means to be under parameterized. And then the other one is to be over parameterized. And the intuition for it, you should recap what you know from linear systems, right? So in linear systems, you also have this, and that's we're gonna actually see again when we talk about the least squares closed form solution, which is gonna come next Tuesday. All right, so I think that finishes the part about cost functions and about linear models. Any questions on this? So I will upload the annotated slides so you can get the PDFs as well. Okay, then, so I will not need the full hour. You can leave a little bit earlier today, but I want to start a little bit with optimization today. And don't worry, like I will upload the slides in half an hour. So optimization is, why do we need this? We need this to do the training. So we need this to now use our cost function to find the best W. So that's what optimization is. And it really continues in the same notation as we had, the same kind of scenario. What we're asking here is we're just trying to find that W which minimizes the overall cost function. So again, maybe I'll write down the cost. So in machine learning and deep learning and anything, it will always be of this form that the cost will be a sum or average of all the data points we see. It's always this form, right? So I will call this ln for the nth data point n. And then, of course, this is all about W, right? Find the best W. W can have, we don't care, here in this chapter, we will not care so much what the model is, if it's a linear or neural network or whatever. It's just some function f which depends on W. So you can have D parameters, you can have D plus 1 parameters, it doesn't matter, so D can be anything. What I just want to ask is, okay, how can I find the minimizer of a function? Can I find this high dimensional vector W, the weights, such that it fits the data and the fit is measured like this? How well, so like this, how well is every data point fit in terms of this cost function that we use? So now we have the cost function, now we're gonna just use it to do training. So because optimizing this, minimizing this, that is what training is, and it's also called estimation or fitting. So what algorithms come to mind to do this? I mean, of course, there's many ways you could do this. So this is this thing is quite general, right? The entire field of optimization is just this, so it doesn't mean much. So it will really depend a bit on the structure. So what kind of function are we optimizing? So the nice thing is in machine learning, we do have a nice structure, and the structure is this one here, that the cost function is always an average over data point. So it kind of decomposes a little bit, that you can look at individual data points separately at training. So that's something that we're going to see later in this when we discuss gradient descent and some variance. So, but for now it is very simple. So I'm just giving a very basic intro to how to optimize a function. And how many of you have seen mathematical optimization already in some of your bachelor courses? Or very good, about half of you. So that's great. But if not, don't worry. So we'll give a bit of a recap, and the perspective is a little bit different in machine learning because of this structure exactly. So, and also we don't have constraints in machine learning. We just solve unconstrained optimization problems like here. And we always have this sum structure. So that's what makes it quite particular and also quite interesting actually. And this is quite important on why machine learning has become to work well on large data sets. It's, a lot of it is also to do, yeah, with this, what is the efficient training algorithm and how to do it practically. How can you run it on a real computer or a graphic card or whatever. So, okay, I'm jumping ahead a bit. So before we go to special graphics cards and so on, so we start a bit more simply to see if I just plot my function, how do I minimize a function? Let's say we have a function of 2 parameters. So maybe W0, W1. It doesn't matter, by the way, how you index your weights, right? Some people prefer to start from 0 to 1, 2. Some people start 0, 1, and so on. So it doesn't matter here because we're not specifying the model. Well, what I'm saying here is that there's a very easy strategy to find a good model, and that is just to try many models. You can try it randomly. You could just say, I'll just randomly initialize some weights. I will check the cost. I will just compute the cost of my W. And then I store it and keep track what's the lowest cost I can obtain. One slightly more systematic way, but equally naive and slow way is to do this in a for loop. I will just do what's called a grid search. So what that means is I will try 3 different values of the first weight, and I will try 3 or 4 different values of the second weight. So you just write a double for loop, right? Because you have 2 parameters, so you want to try all combinations of them. So you start with the first 2 tries, you said. What you do is you compute the cost. So you see that this is if I pick this model, which is my first try, then my data set is fit well or not well. You just compute the value. So you can see the value is 17 as the overall cost function of your data set. So you remember that, and then you go on to the next try and the next one. And every time you compute the cost of the whole data set. So that is quite costly. Namely, you need to feed every data point through the model, get its prediction. Then you see the error between what it should be and what it is. And then you have your cost function. That's ln, and then you sum them up over all data points. So that's what we call that's an entire epoch of training, which is needed to just compute the cost of one model to see how well it fits everyone. Of course, you have to ask everyone, have to ask every data point. So one of these trials is quite expensive, but the interesting thing is here is yeah, like, okay, how many parameters am I trying? And this is going to be a nested for loop, right? So W0, and then you have W1. You also try, you have to specify some interval in which you are confident that the good value must lie in that interval, right? And also you can decide if you want to do this maybe on an exponential scale. That's a good idea, logarithmic scale, or if you want to do it on the natural scale, up to you, and define some boundaries and then write your double for loop. What's the problem with that? Any comments on this? So if I have a yes.
Really work if you have done continuous values for the weights.
Yes, so what you said is that you're saying it doesn't really work so well for if I have continuous values, because I do this discretization of my grid, and you're right. You're saying, I mean, what if I want to minimize the cost, right? So what if my cost function looks like this? So And I don't see that, right? Because I will only try here, and I will try here and here and here. I will not see that there was a big value, which I just missed it because it was not in my resolution. And that's true, that is a problem if you take very few values only. So yes, this is a problem. This problem you could fix by just making a more fine-grained grid, but then of course you're slower, right? So that's okay. And to control this, you can actually use things like to say, you will maybe be able to say that your function is Lipschitz continuous. Even in neural networks, you can say that sometimes. You can see that how quickly is the landscape changing. If you control that, then you can control this a little bit. I would say, I'm just saying that this problem could be probably solved there. So it's not by making more fine-grained steps. There is, however, another problem if I have more than more than 2 parameters I'm searching for. What if I have a large number of parameters? Yes. The complexity goes up, exactly. So yes, that's the main problem if we go to larger parameters d, right? So I just showed you the example of 2, right? But as you said, so if I match more than 2s, then the number of for loops I have to nest into each other is going to be crazy. And the point here is that the number of tries I have to do is exponential in this dimension, because we just ask, like, okay, for 1 dimension, how many parameters do I need to try in my grid? So you found the good grid value for us, that we say that for 1 parameter it's enough to be so fine-grained. So let's say for how many tries per dimension. Let's say we looked at the function and we said that, okay, maybe 10 is enough, and I found boundaries left and right such that 10 is enough. That's fine. So that's here, everything will be 10 grids points per dimension. The problem is there's many dimensions. It's not just 2. So maybe now there's d. So it's 10 to the d, which I have to make. That's how many tries I will do and each one of them I have to check the quality of my model. And 10 to the d is okay for d equal 2. It's not okay if you have many parameters. And model machine learning models really do have a lot of parameters. Even linear regression models, they have millions of parameters. So, and then if d is a number of parameters, so if that's going to the millions, then of course that's completely unthinkable. So this is not going to fly. And this has nothing to do with deep learning or not deep learning. This really has to do with that you cannot search efficiently in a high dimensional space. So this is a huge problem, and this is really something we see. And so this would be kind of a deal breaker, that it tells us you cannot just naively try all the models and pick the best one if you have many parameters. I mean, if you just have 3 parameters, it's kind of fine then. And the same problem will come later when we will talk about hyperparameters, which is some other parameters, and there you actually do it like that. You just try a grid of many random values. But yeah, be very careful if you do this kind of grid search, or the same if you do random search. The exact same problem will come up if I randomly sample in this 2-dimensional plane or in this d-dimensional plane. It's going to fail spectacularly when d goes into the hundreds and higher. So okay, and then the other issue is that, yeah, there is no guarantee if your cost function looks a bit strange. That's the valid point that you raised before, that so if you just do grid search, we cannot give a guarantee that we will surely find a minimizer or not, right? Except if you make other assumptions on the cost function. So for example, for convex cost functions, or ones which are convex and Lipschitz continuous, you can maybe do something, but in general, you will not have a theoretical guarantee. This brings us to just some very basic definitions of optimization on what is the optimum, what is the local optimum. And don't worry, this is going to be easy, but it's important to be precise with this, because otherwise we sometimes it's easy to miss some cases, and it's easy to miss if there may be several optima or there's just one optimum, things like that. But this is very easy. So what I'm plotting here is just that. So in machine learning, we always do this as a function of W, the weights, right? That's what we're optimizing. That's what the training is. So what our overall goal is to find a global minimizer. So it's a global minimum. And actually, so yeah, it's a global minimum, and then because nearby you're in this neighborhood. So actually you are here, right? You're a W vector. If you go slightly left or right, if you go in your neighborhood, the value is worse. Actually, globally it's worse. No matter where you go, you can go arbitrarily far away. It's always going to be worse. So you're strictly the best. That means a global minimum. Whereas a local minimum is something like this here, that you can say, okay, if I go a little bit in my neighborhood, then so if I stay around here, then there's nothing better. So which means the other candidates in my neighborhood are worse or equal. So that's what it means to be a local minimum. So here is the definition. So local minimum means you are not worse than its neighbors. So, and to be precise, we will use an epsilon ball around where you are and say that all the values there are equal or worse than my value. And that's exactly what this means. So we write usually W star. That means that we're talking about something optimal. It's just a naming, right? So W star means something which we think is optimal, at least locally. And what it means is that everyone around us, for all W's which are nearby, epsilon close, they have a worse value than us. So that's a local optimum. Does it make sense? It's very easy. And then the global one, of course, is even easier. That's what global means, right? It means it's the best of all globally. So you're better than every other candidate globally as a W. That's a global minimum. And then very small technicality is that, so some optimum are strict or not. So strict just means that the candidates nearby have a slightly worse value strictly, right? So that the neighbors around you are not equal value. So here it's not, what we have here is not a strict local minimum, because there's neighbors around which are perfectly equal. So these are local minima which are not strict. And this one is a local minimum which is strict, because everyone near the W is strictly higher in the function value. And same here, everyone here is strictly higher when you move. So this is a strict global minimum, and it's also a strict local minimum. So that's this, just a very simple definition. Anything I missed? Any question on this, or clear? Okay, so this we will do mostly next week, but I want to tell you already as a preview that because the grid search was so slow, it was exponentially slow. So there's something better we can do, and the better thing that we do, and which is how all machine learning models are trained basically, is by using gradient descent. So that's what we're gonna want to look at in the next time. And so I'll make it formal when we get to this, but maybe it's good to already think about it in these two examples that we saw, right? So we had W0 and W1, and we asked in the space of two parameters, how do we find a best model, right? We can do grid search in this. So that's what we have done. Try 3 values here, try 4 values there, and try all values. But that's a bad algorithm. So by the way, this cost function here is the mean squared cost function depending on the W's. And the better method is going to work like this. So you are somewhere, you will look at the gradient, which is this thing here, kind of a tangent plane. And that's going to tell you in which direction is it going to go down from where you are. So that's what the gradient tells you. The gradient is just a normal vector of this tangent plane, but in the two-dimensional space where your parameters live. So it's going to tell you a direction where it's going down. So it's going to tell you you should move to the left here. So you're currently located in this W point. And it tells you that you should move to in this diagonal direction towards the whatever left behind or something. So that's what one gradient step will do, and then you will do this again and again. You will compute a new gradient and again go downhill. And next time we were going to look at if there's going to be a difference between. We can try this on the mean absolute error. We can try this on the mean squared error. We can try this on any model you have, combined with any cost function you have. You could do gradient descent to find the best W in your W space. So that's what we're going to do next week. And with that, let's finish 5 minutes earlier. See you next week.